This is Professor Mark Barkey from the University of Alabama. We're going to continue on today talking about plasticity, in particular about deformation theory plasticity or total strain theory plasticity. And in the case of the von Mises yield criterion as our yield function, or J2, the Hencky equations. We're going to talk a little bit about proportional versus non-proportional loading. And we're going to show this identity that SMN dSMN is equal to SMN d sigma Mn, where S is our deviatoric stresses, and we've used our summation notation that's implied through our index notation. Of course, d sigma Mn are regular stress increments, and dSMN are deviatoric stress increments. Let's talk a little bit about proportional versus non-proportional loading first. And for that, I'm going to see if I can call up a screen. There we go. And in this plot, I have plotted sigma versus tau. So I'm in a stress space, sigma versus tau stress space. And I want to get to a certain endpoint. I want to get to a certain endpoint of sigma and tau that is above the elastic limit, so we have some plasticity. So this is some stress level where we have some plasticity. Of course, if this was just uniaxial or just pure torsion, we could look at our stress strain curve and see what kind of plastic strains that we have. But we have a combination of tension and torsion. And so path A, if you notice, it's going through the origin and going up to this point in a straight line fashion. That is known as a proportional loading path. Proportional in the mathematical sense is something that is a straight line in this space. All the stress components are proportional to one another, and they maintain that constant of proportionality throughout their entire history. And it also has to go through the origin, strictly speaking. Now, we can see that in cyclic loading sometimes we can have some mean stresses and we can still deal with some offsets and things like that. But in very strictly, proportional loading is a loading path that goes through the origin, and it is maintaining a straight line in our stress space. Anything else is a non-proportional loading path. Now, there can be all kinds of variations on this. I've drawn one in here, this path B. It starts off with a little bit more tension than shear, and then towards the end has more shear than tension for the increments of stress. But any path that is not along the proportional path is a non-proportional path. So, for example, we could hold our tension, we can increase our tension while maintaining zero torsion, and then hold that tension and then increase the torsion up to this point. Or conversely, we can go and we can have no tension, but we can increase our shear and then bring this over, holding the tension constant and now increasing the shear. But we'd end up at this spot in the end. So let's show a couple notes on that. Alright. So path A is proportional loading, linear or proportional relationship among the stress components, and it goes through the origin. Any other path, for example path B, is a non-proportional loading path. And the reason why we want to make this distinguishing feature between proportional versus non-proportional loading is that plasticity is path dependent. Depending on where we end up, we may end up at the same spot, but depending on how we get there, we may end up with different strains, different plastic strains from those two different paths. So if I take a stress increment d sigma ij for path A, that would be this one right here, and I have a different stress increment that goes over here. Now these are finite increments. We talked about incremental plasticity representing small changes as finite increments. For each small change in stress, as we get to this point, we have a small change in plastic strain that we add up and accumulate to get to the final plastic strain at this particular point. And for path B or any non-proportional loading path, we have a different small change in stress that gives us a different amount of small change in plastic strain, and then we finally end up at the same point. But in general, the final plastic strain state for path A is not equal to the final strain state for path B. We do have this path dependency. Now what we can do with deformation theory plasticity is, if we know the path that we're going to follow, we can do a closed form path integration and come up with some equations that'll just tell us what the final strain state is at the end. Now in general, this works for paths that can be easily defined, and we can do this closed form integration for. We can do this closed form integration for paths that are non-proportional too, but those typically tend to be a little bit more difficult. For a general plasticity algorithm, which is what we're trying to implement here, in general we would want to use the incremental plasticity formulation. However, for these proportional loading paths, it is extremely convenient that if we know we have proportional loading, to use the closed form pre-integrated equations. So let's take a look at our incremental plasticity, and then we'll see how to do a closed form integration for this particular path. And let's start out with our normality flow rule, where we have defined this already previously, but the plastic strain increments d epsilon tensor p is equal to d lambda n dot d sigma n. N dot d sigma is a scalar. D lambda is a scalar that's equal to 3/2 1 over h, where h is our plastic tangent modulus. If we were to show our stress versus plastic strain curve, and at a particular point on this, we could take a look at a small increment of stress and a small increment of plastic strain from our uniaxial test. Then h would be defined in the finite interval delta sigma over delta epsilon p, and at a particular point in an infinitesimal, we could have d sigma over by d epsilon p. Okay. So our d lambda then is going to be this 3/2 1 over h 1 over d sigma d epsilon p. Well, let's talk about our normality flow rule again. We're going to write these terms out, and then we'll talk about how to do that closed form integration. Okay. So if we consider isotropic hardening, and the same thing applies for kinematic hardening with the shift tensor, our alpha in there. If we look at our yield surface in deviatoric stress space, we know how we can find our unit vector n. Okay, so from our origin of deviatoric stress space to here, we're going to call this vector psi. But if we're in using isotropic hardening, this is the same as the deviatoric stress S, deviatoric stress tensor S. So in general, it's S minus alpha, but for isotropic hardening, our alpha is equal to 0. Just going to make this a little bit more convenient for us to deal with. So let me just make a note here. This is for isotropic hardening. Now, the convenience of working in deviatoric stress space is that we have a hypersphere in our J2-based plasticity theory. So our unit normal is the magnitude of xi, xi divided into the magnitude of psi. Right? So our n is going to be, in this case, S divided by S dot S. And we've talked about this before. The radius of our yield surface is square root of 2/3 sigma naught. So this n is going to be S. This is the magnitude squared, so this would be 2/3 sigma naught squared. So if I want to, what I can do for my normality flow rule in terms of the increments, if I use my index notation, d epsilon ij plastic is equal to d lambda n dot d sigma times n. Oops, and before I go too far, I don't want s dot s dot on the bottom. What I want is I want this to the 1/2 power. So this is actually the 1/2 power, and so is this. So that when I put these together, I have d lambda s m n d sigma m n times s I j, and then when I put these together, then I end up with a 2/3 sigma naught squared down on the bottom. If I put in my expression for my plastic tangent modulus, I can have the 3/2 1/h smn d sigma mn over this 2/3 sigma naught squared, and now my Sij. Alright, now let's take a look at that term on the top that has the summation in it. This term right here. Smn d sigma mn. And what we're going to do is we're going to show that that's going to be equal to Smn dsmn. Okay, so we'll get back to this here in just a second. Let's take a kind of a brief interlude, and we'll figure this part out. All right. So let's start with Smn dsmn. By the definition of deviatoric stresses, we can figure out what that is. Okay, now remember, deviatoric stresses, let's write this as Ij, I guess. Sij is equal to sigma Ij minus 1/3 Kronecker delta Ij sigma Kk. So in terms of increments, dsmn is equal to d sigma Ij minus 1/3 Kronecker delta Ij d sigma Kk. And let's see, well, I used m and n, so in this expression I really should change that to m and n in here. Now if I multiply these terms out, I get Smn d sigma mn minus 1/3 Sm, it's an S, Smn Kronecker delta mn d sigma Kk. And because the Kronecker delta can act as a replacement operator on indices, I can replace this with Smm d sigma Kk. But Smm is the trace of the deviatoric stress tensor. It is equal to 0. So we have shown what we wanted to show, is that d is Smn d Smn is equal to Smn d sigma mn. Now, keep in mind, I'm not saying that the stress increment d sigma is equal to the deviatoric stress increment ds. What I am saying is that the summation of Smn d sigma mn is the same as the summation of Smn d Smn. Okay, so be careful about that. Make sure you have a good understanding of how index notation works. Alright, now let's look specifically at the J2 criterion. If our yield function f is equal to 1/2 Sij minus 1/3 sigma naught squared, and if we want to take the derivative of that, well, in general terms, we would have partial derivative of f with respect to s ds minus the partial derivative of f with respect to sigma d sigma equals 0 to satisfy our criterion. But if we have our specific J2 criterion, then we would have Sij d Sij equal to 2/3 sigma naught d sigma naught. And by our index notation, because these are dummy indices, this is the same as the expression Smn d Smn. So our expression on the previous page, 3/2 1/h Smn d sigma mn over 2/3 sigma naught squared Sij. We can rewrite that as 3/2 1/h. Now let's see, Smn d Smn for 2/3 sigma naught squared times Sij. And now that we know what Smn d Smn is equal to, we can put that in there as well. Right. So we can put this in here. This summation is equal to 2/3 sigma naught d sigma naught divided by 2/3 sigma naught squared Sij. Of course, now we can get some things to cancel out. Three halves 1/h d sigma naught over sigma naught times Sij. Alright, now if we interpret this plastic tangent modulus as a slope, we can rewrite 1/h as d epsilon p by d sigma naught. And then on the top we have the d sigma naught over sigma naught Sij. And as first order increments, we can then rewrite this as 3/2 d epsilon p over sigma naught Sij. Now at this point, it's helpful to remember what these terms are. Sij, of course, is our deviatoric stress components. The epsilon ijp is our plastic strain increments. Sigma naught is our equivalent stress, in this case our von Mises stress. It's related to the size of our yield surface in our deviatoric stress space. And this d epsilon ijp, it comes from our equivalent stress strain curve. All right, now let's consider a proportional loading path. And to define the proportionality now, what I'm going to say is that our stress state, sigma, this tensor, is equal to some reference stress state times some proportionality constant. So we can factor this constant A out in front of any term, every term in this stress tensor. Okay, and A is a monotonically increasing scalar function of time. So if this applies to the stress tensor, it also applies to the deviatoric stress tensor, where we define the deviatoric stress reference tensor as S star. We still have that same constant. It also scales with the size of our yield surface. So if we're at a certain size of our yield surface, sigma naught, now I know we're off by a scalar, but if we're at equivalent stress, sigma naught, then this also scales up to A times sigma naught star. Right, so if we look at this then for the increments, d epsilon I j plastic is equal to 3/2 d epsilon p over sigma naught Sij. But because sigma naught is equal to A sigma naught star, S is equal to A S star, so we have 3/2 d epsilon p for A sigma naught star times A Sij star. Of course, the A's cancel out on the top and the bottom. And what we see then is that it's not the values of the stresses, but it's the accumulated plastic strain increment that'll be important when we want to find our final strain state. So the fact that the ratio of Sij star to sigma naught star stays constant for all time means that if we want to find epsilon ijp, and really what we want to do is we want to have 3/2 Sij star over sigma naught star times an integral of d epsilon plastic. Typically this is written this way, Sij over sigma naught times epsilon p. And for the J2 theory, these are known as the Hencky equations. This epsilon p can be read directly from a stress strain curve, stress plastic strain curve. So you enter in the value of your equivalent stress, sigma naught, and then you come down here and you read the value of epsilon p. It's very easy to apply. And for our Ramberg-Osgood equation, if we use that material description, then we have our epsilon p is equal to sigma naught over k to the 1 over n power. Let's go ahead and write down what these different terms are for the different components of plastic strain. So epsilon x plastic will be equal to 3/2. I'll write it this way, just epsilon p over sigma naught Sx. Epsilon y plastic is 3/2 epsilon p over sigma naught Sy. Epsilon z plastic is equal to 3/2 epsilon p over sigma naught Sz. And then we have to be a little bit careful about our shearing strains. These are tensor shearing strains, so epsilon xy plastic is equal to 3/2 epsilon p over sigma naught Sxy, same as tau xy. And then let's go ahead and write down these other two just so we have them. Epsilon plastic xz is equal to 3/2 epsilon p over sigma naught Sxz. And for yz, we have Syz. Alright, of course, just write it down. Sij is equal to sigma ij minus 1/3 sigma kk Kronecker delta ij. And if we want to find our elastic strains, we just use Hooke's law. So for example, epsilon x elastic is equal to sigma x over E minus nu sigma y over E minus nu sigma z over E. And you have your other two equations. And the tensor shearing strain, epsilon xy E is equal to tau xy over 2g. And then, of course, gamma xy would be equal to 2 epsilon E xy plus 2 epsilon plastic xy. Alright, so you'll see me do an example that I have later in this playlist where I do a proportional loading path and I check my work using these Hencky equations, and I think you'll see that they match pretty well. Alright, finally, just to say again, you want to use these deformation theory plasticity equations. That's what they're called in general, specifically for the J2 failure theory that we're emphasizing in these lectures, called the Hencky equations. You can only use those for proportional loading paths. They give you these very nice and easy to use closed form equations. Again, the way that you use them is you calculate your current von Mises equivalent stress. So if you're having isotropic hardening, it could be a high level, whatever stress level you're at. You find your von Mises equivalent stress. You find your corresponding plastic strain, for example, using our description of our stress strain curve from the Ramberg-Osgood equation. You take that and you multiply it by 3/2 of Sij, where Sij is a deviatoric stress. only affects the normal stress components, sigma ij minus 1/3 sigma kk Kronecker delta ij. You can find your plastic normal strain components and your plastic shearing strain components, keeping in mind that these are tensor shearing strains. You can find your elastic strain components from our isotropic material assumption Hooke's law, using Poisson's ratio and the modulus of elasticity. And you can find your elastic shearing strain components using the shear modulus. Of course, our assumption here that it is isotropic material, so G is equal to E over 2 divided by 1 plus nu. And then finally, our total strain, shearing strain, for example, would be gamma xy is equal to 2 tensor strain epsilon xy plus 2 epsilon pxy. And let's go ahead and write it down here. Our total strain epsilon x would be equal to our total elastic strain epsilon xy, epsilon xx. Or just epsilon x. Elastic plus epsilon x plastic. Alright, so that does it for this, and maybe I'll try to fill in a couple gaps with some examples at a later time.